how water moves in the Earth's atmosphere, and also how it gets there and how we measure it. So the first bit will be some review, and then there'll be some new material. So to start, we'll look at the water cycle. This should be a review for most of you. This shows how water moves between the Earth and its atmosphere. Right? So since it's a cycle, right, there's no real beginning or end, so you can kind of start anywhere and it just loops all the way around. So we have evaporation, liquid water becoming a gas into the air, right? And water vapor is, of course, a clear, colorless gas. We can't see it, we can't taste it, we can't smell it. Condensation, that water vapor turns back into a liquid, and that's key. That'll be really important when we look at clouds later this week. Precipitation, water droplets bunch up and fall to Earth, and then runoff or infiltration, the water flows either on the surface into a stream or soaks down into the ground and becomes part of the groundwater. So those are the basics of the water cycle, just to review. What we're going to focus on today is humidity, which is the amount of water vapor in the air. Right? If we have more water vapor, we have more humidity. Where it gets a little tricky is that air can only hold so much water vapor. Right? And this makes sense. You can't have an infinite amount of water vapor in the air. We can't just keep evaporating water forever. It turns out that warmer air can hold more water vapor than cold air. So if you have two equal amounts of air, the warm air could hold more water vapor than the cold air. It doesn't mean it has to, it just means it's able to. And the reason is because those water molecules, or those air molecules rather, are moving around really fast. They've got lots of energy, so they can absorb more water. But when we measure humidity, we always talk about, and you'll hear on the weather, we always talk about relative humidity, right? And it's a percent. And this measures how much water the air has compared to how much it could hold at that temperature. Right? So let's say I have a cubic meter of air, right? So that's a volume of air 1 meter on a side. So picture a cube 1 meter on a side. Say that it could hold 10 grams of water vapor at most. If it only holds 5, then we would say, if right now it's only holding 5, we would say that the relative humidity is 50%, right? That air could hold 10 grams of water vapor at the temperature it's at, but it currently has 5, which makes the relative humidity 50%. And so a lot of times what I'll use for the rest of this is to kind of visualize it. You can picture a box where the box represents the maximum amount of water possible. Right? So this box represents the most water vapor that the air could hold, and the blue dots represent water vapor actually in the air. So these blue dots are water vapor that's currently in the air. The box is the maximum it could hold. And so based on this picture, we can see that the relative humidity in this example is, once again, 50%. Right? It's about a half full. So how can we change relative humidity, or how does relative humidity go up or down? There's two ways to do this. We can either change the amount of water vapor. That's pretty straightforward, right? If you have more water vapor in the air, you're going to have more relative humidity, right? The other way to do it is to change the temperature. And if you change the temperature, if you increase the temperature, not changing anything else, the relative humidity actually goes down. And we're going to use that box diagram to explain why again. So let's talk about changing water vapor. Again, the box is the maximum amount of water possible. Blue dots represent water actually in the air. Currently, our relative humidity is 50%, right? And that should be clear. We have half of the box full. But if I were to double the amount of water vapor actually in the air, as soon as it catches up, if I were to double that amount of water vapor, now, oh gosh, there we go, let's leave it there. Now, we're much closer to 100%, right? I have more water vapor, so I have increased my percentage. So now, my relative humidity is closer to, we'll call it probably 95%. Right? It's much closer, not quite full, there's a little bit of space at the top, but there's more room. Right? If I were to delete water, water would go away, then our relative humidity would go down. So hopefully that's pretty straightforward. Well, let's take a look at what happens if you change the temperature. Again, we'll go back to our original starting position. Right? Box represents the maximum amount of water possible. Blue dots represent water vapor actually in the air. So right now, again, as a start, my relative humidity is 50%. Let's say my air cools off. It gets colder. Based on what we talked about earlier, that means it holds less water vapor. Since the box represents the maximum amount of water possible, if I can hold less water vapor, my box will have to get smaller. Right? So this amount, and it gets a certain amount smaller. My relative humidity now, even since my amount of water hasn't changed, I'm now probably closer to maybe 70%. Right? Because right now, this water is taking up 70% of the available space. If it were to get a lot hotter, right, the air would be able to hold more water vapor. At this point, I'm now closer to maybe 30%. Right? The amount of water hasn't changed. I still have the same amount of water in the air. All that's changed is the amount of water that the air could hold. Right? And so that's important to remember. Alright, tomorrow we'll do a lab where we will measure the relative humidity of a classroom. So please write 3 questions at the bottom of your notes, and I'll see you guys tomorrow.